Picture yourself floating in space, approaching the most mysterious object in the universe, a black hole. As you drift closer to this cosmic behemoth, reality itself begins to unravel around you. Time starts flowing like molasses, slowing down with each passing moment. The stars behind you appear to shift and stretch, their light bending in impossible ways as space itself warps and twists. You've crossed the point of no return, the event horizon, where even light cannot escape. As you continue your descent into this cosmic abyss, the laws of physics as we know them begin to break down one by one. Einstein's equations, which have served us so well in understanding the universe, start to falter and fail. The very fabric of space-time stretches and contorts like a piece of rubber being pulled to its breaking point. What lies at the heart of this cosmic monster? What happens when we reach the point where the fundamental rules governing our universe cease to make sense? Today, we're embarking on a journey to explore the greatest mystery in all of cosmos, the singularity at the center of a black hole. This isn't just another astronomical phenomenon, it's the ultimate boundary where our understanding of reality itself comes to an end. In the next few minutes, we'll venture into a realm where infinity isn't just a mathematical concept, but a physical reality. A place where matter is crushed to infinite density, where time might flow backwards or cease to exist altogether, and where the very mathematics we use to describe the universe breaks down completely. This is more than just a journey through space. It's an expedition to the very edge of human knowledge, to a place where physics as we know it waves a white flag of surrender to the unknown. Welcome to our exploration of the most extreme object in existence, the singularity, the heart of darkness that lurks within every black hole. Buckle up, because we're about to challenge everything you thought you knew about the nature of reality itself. At its most fundamental level, a singularity represents the ultimate puzzle in modern physics, a mathematical point of perfect nothingness that somehow contains everything. Imagine taking all the mass of a star, many times larger than our sun, and compressing it into a point so small it has no dimension at all. It's a concept that challenges not just our understanding of physics, but our very ability to comprehend reality. As Nobel laureate Dr. Kip Thorne explains, a singularity marks the point where our current understanding of physics completely breaks down. It's not just that our equations become difficult to solve, they actually become meaningless. Picture yourself trying to divide any number by zero on a calculator. The error message you get isn't just a limitation of the calculator, it represents a fundamental mathematical impossibility. That's similar to what happens when we try to describe a singularity using our current physical laws. The best way to visualize a singularity is to think of it as a cosmic hurricane's eye, but one that defies all natural laws we know. In a normal hurricane, the eye is the calmest part, but in a singularity, it's quite the opposite. It's where everything reaches infinity. The density becomes infinite. The curvature of space-time becomes infinite. The gravitational force becomes infinite. It's as if reality itself is being stretched to breaking point and beyond. Think of the fabric of space-time as a rubber sheet. Now, place a bowling ball in the center. It creates a depression, a curve in the sheet. A singularity is like placing an object so massive that it doesn't just curve the sheet, it punctures through it entirely, creating a bottomless well in the fabric of the universe itself. But unlike a real sheet with a hole, this cosmic puncture doesn't lead anywhere we can comprehend with our current physics. The matter that falls into a singularity becomes compressed to such an extreme degree that the atoms themselves are crushed out of existence. The normal space between atomic nuclei and electrons, between quarks and other subatomic particles, is completely eliminated. What remains defies our understanding, a point of zero volume but infinite density, where space and time cease to have any meaningful definition. This is why singularities are so fascinating to physicists and cosmologists. They represent the absolute edge of our knowledge, the frontier where Einstein's theory of general relativity collides head-on with quantum mechanics, and neither emerges victorious. They might hold the key to understanding how these two fundamental theories of physics can be unified, potentially revealing new laws of nature that only become apparent under such extreme conditions. When we discuss the physics of a singularity, we're venturing into a realm where our conventional understanding of nature completely collapses. Let's try to grasp just how extreme these conditions are. Imagine taking our entire planet Earth, all its mountains, oceans, cities and core, and compressing it down to the size of a pinhead. That's already mind-bending, isn't it? But a singularity goes far beyond that. Now imagine compressing that pinhead-sized Earth even further, continuing to squeeze it smaller and smaller, past the size of an atom, past the size of a proton, until it occupies literally no space at all. This isn't science fiction. It's what Einstein's equations tell us must happen inside a black hole. The gravitational force at a singularity is so immense that it breaks down the very structure of matter itself. Atoms are torn apart. The nuclei of those atoms are shredded. Even the fundamental particles that make up protons and neutrons are crushed out of existence. Nothing we know of can resist this ultimate compression. The force involved is so intense that our mathematics can't even describe it without reaching infinity. And infinity in physics usually means our equations have failed us. Einstein's field equations, which normally describe gravity with beautiful precision, reach a breaking point at the singularity. When we try to calculate the curvature of space-time at this point, our equations essentially try to divide by zero, a mathematical impossibility. Yet unlike a simple mathematical error, this represents a real physical phenomenon. It's as if reality itself is being divided by zero, creating a rift in the fabric of space and time. To understand how dramatic this breakdown is, consider this. At a singularity, the normal rules of cause and effect may cease to exist. Time itself might stop having meaning. The distinction between past and future could blur or vanish entirely. The three dimensions of space we're familiar with might collapse into something our minds can't even conceive. This is why physicists often say that the known laws of physics break down at a singularity. They don't just bend or stretch, they completely cease to function. The most perplexing aspect is that these aren't just theoretical musings. According to our best understanding of physics, singularities must exist inside black holes. Every black hole contains this point where physics breaks down, hidden behind an event horizon. It's as if nature itself is telling us that there are places in our universe where our current understanding of reality is simply inadequate. This brings us to one of the most profound questions in modern physics. What new laws might govern the behavior of matter and energy at a singularity? What deeper principles might emerge when our current theories fail? These questions drive some of the most cutting-edge research in theoretical physics today, as scientists attempt to reconcile quantum mechanics with gravity and understand what happens when space and time themselves break down. If you're having your mind blown as much as I am with this information, hit that like button and subscribe to the channel for more content that will make you rethink everything you know about the universe. Stephen Hawking, one of humanity's greatest minds, dedicated much of his life to unraveling the mysteries of singularities. His groundbreaking work with Roger Penrose in the 1960s proved that singularities weren't just mathematical curiosities, but real predictions of Einstein's theory of general relativity. Hawking's fascination with these cosmic enigmas led him to propose that in the extreme conditions of a singularity, entirely new laws of physics might emerge, laws that remain hidden in the normal universe but become dominant when space-time breaks down completely. What makes these potential new laws so intriguing is that they might help resolve the apparent loss of information in black holes, a paradox that troubled Hawking for decades. He suggested that these laws might govern how information is preserved when matter falls into a black hole, possibly through subtle quantum effects that become important near the singularity. This could mean that nothing is truly lost to a black hole. It's just transformed in ways our current physics cannot describe. Some theoretical physicists have proposed even more exotic possibilities. They speculate that singularities might serve as cosmic bridges, connecting different regions of our universe, or perhaps even linking to entirely different universes. This concept, sometimes called a white hole, suggests that matter falling into a black hole singularity might emerge somewhere or somewhen else. While this remains highly speculative, it highlights how singularities might be more than just cosmic dead ends. Perhaps the most radical interpretation comes from string theorists and quantum gravity researchers who suggest that at the singularity, reality itself might unravel into its most fundamental components. They propose that space and time as we know them might dissolve into more basic building blocks, perhaps strings of energy vibrating in multiple dimensions or quantum bits of information in a cosmic computer. In this view, a singularity isn't so much a point of infinite density as it is a place where reality itself is reduced to its most elementary form. Even more fascinating is the possibility that singularities might be nature's way of telling us something profound about the structure of our universe. Some scientists propose that the very existence of singularities in our mathematical models might be pointing to a deeper truth, that space and time themselves are not fundamental, but emerge from something even more basic. This could mean that when we finally understand singularities, we might discover that reality is far stranger and more fascinating than we ever imagined. The quest to understand singularities continues to drive theoretical physics forward, pushing us to develop new mathematical tools and conceptual frameworks. Whether they turn out to be gateways to other universes, points where new physics emerges, or something even more exotic we haven't yet imagined, singularities remain one of the most profound mysteries in modern science. They stand as cosmic question marks, challenging our understanding of the universe and promising that there are still fundamental secrets waiting to be discovered in the depths of space and time. The implications of singularities stretch far beyond their role as cosmic curiosities, touching upon the very foundations of our understanding of reality. If we could somehow observe a singularity directly, a feat prevented by the black hole's event horizon, we would be witnessing something unprecedented, the absolute boundary where physical reality as we know it ceases to exist. It would be like peering over the edge of creation itself, seeing where the laws of physics draw their last breath. The event horizon acts as a cosmic censor, forever hiding the singularity from our view. This censorship, which Roger Penrose formalized in his cosmic censorship hypothesis, might actually be nature's way of protecting us from the breakdown of physics itself. It's as if the universe has drawn a veil over regions where our current theories predict their own destruction, preserving the predictability of physics in our observable universe. Perhaps the most profound implication of singularities lies in their potential to unite two seemingly incompatible pillars of modern physics, quantum mechanics and general relativity. Roger Penrose, who won the Nobel Prize for his work on black holes, suggests that singularities might be the key to achieving physics' holy grail, a theory of quantum gravity. This unified theory would bridge the gap between the quantum world of the very small and the gravitational realm of the very large, a reconciliation that has eluded physicists for nearly a century. The necessity for such a unified theory becomes glaringly apparent at singularities, where gravitational forces become so intense that quantum effects can't be ignored. In these extreme conditions, space-time becomes so warped that the usually distinct domains of quantum mechanics and gravity become inseparable. Understanding how physics behaves at singularities might reveal the deep connection between these fundamental forces, potentially revolutionizing our understanding of the universe's basic architecture. This quest for unification has profound philosophical implications as well. If we can understand how physics behaves at singularities, we might gain insight into the origin of our universe itself. After all, the Big Bang shares many characteristics with black hole singularities, suggesting that the birth of our universe might be better understood by studying these cosmic extremes. Some theorists even propose that black hole singularities might give birth to new universes, suggesting a kind of cosmic reproduction where each black hole becomes the seed of a new reality. The implications extend into the nature of time itself. Near a singularity, time as we understand it begins to break down. This breakdown might reveal whether time is truly fundamental to reality or merely an emergent phenomenon, a question that cuts to the heart of our understanding of existence. Some theorists suggest that the behavior of time near singularities might help us understand why time appears to flow in only one direction in our everyday experience. These implications also raise profound questions about determinism and predictability in physics. Classical physics suggests that if we know the state of a system at one time, we can predict its future states. However, singularities represent a fundamental limit to this predictability. Information that falls into a black hole appears to be lost forever, challenging our notions of cause and effect and suggesting that perhaps the universe is not as deterministic as classical physics would have us believe. Understanding singularities might also help us grasp the limits of scientific knowledge itself. They represent points where our current mathematical frameworks break down completely, forcing us to confront the boundaries of human understanding. This might lead to new ways of thinking about physics, perhaps requiring us to abandon some of our most cherished notions about space, time, and the nature of reality itself. The implications of singularities thus touch upon every aspect of fundamental physics, from the nature of space and time to the basic structure of reality. They stand as cosmic laboratories where the most extreme conditions imaginable might reveal the deepest truths about our universe, potentially leading to a revolution in physics as profound as any in human history. As we reach the end of our journey into the heart of black holes, we're reminded of a profound truth about science and human knowledge. Singularities stand as cosmic monuments to the limits of our understanding, humbling reminders that despite our remarkable technological advances and mathematical insights, the universe still holds mysteries that defy our comprehension. From the curved space-time of Einstein's relativity to the quantum fluctuations of the subatomic world, our scientific achievements have unveiled countless secrets of the cosmos. Yet here, at the center of black holes, we find ourselves standing at the edge of knowledge itself. These cosmic enigmas serve a greater purpose in the scientific endeavor. They remind us that science is not merely a collection of answered questions, but a continuous journey of discovery. Each answer we uncover leads to new questions, each solution reveals new mysteries, and each breakthrough opens doors to unexplored territories of knowledge. This perpetual frontier of discovery is what makes science such a captivating pursuit. It's a testament to the boundless nature of human curiosity and our relentless drive to understand the cosmos we inhabit. Singularities particularly exemplify this endless frontier. They challenge our most sophisticated theories, push the boundaries of our mathematical frameworks, and force us to question our fundamental assumptions about the nature of reality. Yet rather than discourage us, these challenges inspire new generations of scientists to push further, think deeper, and imagine more boldly than ever before. They remind us that the greatest discoveries might still lie ahead, waiting for new minds with new ideas to unlock their secrets. As we conclude our exploration of these cosmic mysteries, I invite you to continue this remarkable journey of discovery with us. If you've found yourself captivated by the profound mysteries of singularities and the endless frontier of cosmic exploration, don't miss out on future adventures into the unknown. Subscribe to Exploring the Universe and become part of our growing community of cosmic explorers and knowledge seekers. By joining our channel, you'll embark on regular journeys to the furthest reaches of space and the deepest mysteries of physics. From quantum mechanics to dark energy, from the birth of stars to the death of universes, we'll explore together the most fascinating phenomena our cosmos has to offer. Hit that subscribe button now, enable notifications, and ensure you never miss our next venture into the unknown. Remember, every great scientific breakthrough began with curiosity, the same curiosity that brought you here today. Share this video with fellow science enthusiasts who might be equally fascinated by these cosmic mysteries. Leave your thoughts and questions in the comments below. Your perspective might spark the next great discussion about the nature of our universe. Let's continue this cosmic journey together, pushing the boundaries of knowledge and understanding. Because in the end, it's not just about the answers we find. It's about the questions we dare to ask and the mysteries we dare to explore. See you in our next cosmic adventure through the wonders of space, time, and everything in between.